Hello and welcome to the module 555 timer operation. In this module we'll be going over a few of the other RC constants that we need to design in order to get our 555 one-shot speed sensor circuit working. We've already gone over the motor, which we've solved in a previous lab. Additionally, in class we looked at the 555 one-shot itself. What we still need to design are our trigger circuitry as well as our low-pass filter circuitry. If you'll recall, our trigger circuit has an input of our encoder output. That's this 50% duty cycle square wave coming from our encoder, and this is applied to our trigger circuitry, which is then input to our 555 timer. Inside of our 555 timer there's a comparator which compares our trigger output to a voltage of 1/3 of VCC to generate a set pulse for the internal RS flip-flop. That set pulse should look something like we see down here. Now as this circuit is operating, it transitions through 4 different states. We've highlighted these with the red lines on the plot over here. Initially, our first state, VCC is high. We have our encoder signal sitting at 5 volts, trigger is sitting at 5 volts, and our capacitor is sitting at 0 volts. In this state we can draw an equivalent circuit seen down here. This is our first equivalent circuit. We have an encoder at 5 volts, we have VCC at 5 volts, and our capacitor voltage is 0 volts. Now if we add up the voltages on the right side of the circuit over here, we have 5 volts plus 0 volts. You'll see that this node right here is sitting at 5 volts, meaning we have 0 volts across our resistor. Now our first transition comes when encoder drops low, and you can see that right here. This is the first red line when encoder drops low. Now as soon as that happens, we're going to transition into a new state, and so we'll have a new equivalent circuit. You can see the second equivalent circuit right here, and you'll notice that once encoder drops low, we now have 0 volts on this side of the capacitor, meaning that our capacitor is equivalently directly attached to ground. Now VCC is still 5 volts, but in this state our capacitor voltage is transitioning. And so this is one we'll analyze in a little bit more detail later, because it'll set the timing for our trigger pulse. In any case, we're going to have the capacitor voltage continually increasing through this state. Eventually, our capacitor voltage is going to reach 5 volts as that resistor charges it up from 5 volts. And when that happens, we transition into a new state, as seen by this third equivalent circuit. In this state, we have a constant capacitor voltage of 5 volts, a constant supply voltage of 5 volts as well, and you can see that's directly applied across our resistor so that we have 0 volts across that. Our last transition comes when our encoder pulse transitions high again. You can see that on this second red line up here. So we're now transitioning encoder from low to high. Now what that's going to try and do is push our trigger node above 5 volts. And you can see that in our fourth equivalent circuit. As soon as encoder jumps high, we now have 5 volts here. We already have 5 volts across our capacitor, and so if we add up these voltages on this side, we have plus 5, we have 10 volts from there to ground. And that's where our diode comes into play. Our diode is going to short that voltage through the diode. It's going to short these two nodes right here, and it's going to ensure that our VCR node right here, which turns out to be our trigger node, stays at 5 volts and doesn't transition any higher. Now because encoder is forced to be 5 volts, and we've shorted this to 5 volts, that means our capacitor is going to end up with 0 volts across it. And you can see that in our waveforms as VC1 transitions down to 0. So these are the 4 states that happen. 2 of them are really steady state circuits. We have our first equivalent and our third equivalent here. Those are just when the circuit is sitting around, so we don't need to analyze them anymore. Our last state we see here, we know what happens. The node tries to transition too high, and our diode shorts the voltage out. But we don't really care about that because it's not setting any of our timing. So we can ignore this fourth equivalent circuit as well. The one we need to analyze in a little bit more detail is this second circuit right here, because this is going to determine the timing of our trigger for our 555 timer. Now in class we analyzed a very similar circuit to this, and we're going to use the exact same procedure we did there. First of all, we'll notice that we have a single node on our circuit, and so we can write node equations into that. We have current flowing this way, and then current flowing down that way. We end up with 5 volts minus Vc1 over R1 equals C dVc1 dt. And you should recognize this. This is pretty much the exact same as what we got before. Because of that, we can just write our answer directly, and we're going to jump to Vc1 equals 5 volts plus some constant times e to the minus t over R1 C1. Of course, we've left a in here because our initial conditions may be different. So if we take a look, what's the value of Vc1 at time 0? Well, it turns out that 0, our initial conditions are the exact same as before. So we can simply write the solution as Vc1 equals 5 times 1 minus e to the minus t over R1 C1. And here we can double check. We have a t over an r times a c. R times c has units of seconds, t has units of seconds. It cancels out. Additionally, we're multiplying a unitless quantity and 1 minus a unitless quantity. So unitless quantity multiplied by 5 volts, we're going to end up with a voltage, which is the units that we want. So once we've solved for that equation, now that we've solved for the voltage at that node, we can take a look at how the timing works out. And if you remember, the internals of our 555 timer mean that trigger is going to be high as long as this voltage is below 1/3 of VCC. So we're going to solve for what point in time does this voltage reach VCC over 3. So we're looking for VC1 at time t trig equals VCC over 3. And we solve this in the exact same way as we did in class. You end up with VCC over 3 equals VCC times 1 minus e to the minus t trig over R1 C1. And if you solve it out, you'll end up with t trig equals R1 C1 times the natural log of 3/2. So you can work that out, but it works the same way as we did in class. And now we select R1 and C1 to set how long t trig is going to be. Remember, we want that to be somewhere between 1 to 5, maybe 10 microseconds. And so at this point, we've solved nearly all the blocks we need to. We know exactly how our motor operates. We now know how to go from a 50% duty cycle encoder waveform to these short pulses, or the waveform which is going to get us these short pulses with our trigger circuitry here. We then know how the 555 works from our in-class discussion. And finally, we simply need to know how to go from this pulsing waveform on the output of our one-shot to the constant waveform that we're looking for on the output of our low-pass filter. Now the low-pass filter is one of the more complicated blocks, and you realize that it looks pretty much like the other ones we've used. We have a single R and a single C here. And so we might think of analyzing it the same way. And we'll see pretty soon that that leads to a little bit of trouble. But just as we start out, let's reiterate what the inputs and the outputs to this circuit are. The input to our low-pass filter is actually the output of our 555, and that's going to look something like this waveform here. It's going to have some duty cycle, And by duty cycle, I mean the ratio of the on time to the full period. And it's going to be pulsing, and we'd like to average that with our circuit in order to get this constant output. We want this output to be proportional to the speed of our motor, because it'll be the average of this variable duty cycle waveform. So that's what we're looking for. But how do we analyze this? How do we choose R3 and C3 so that we get an acceptably flat output voltage given this pulsating input voltage? To start off, we can look at the states that this circuit goes through and draw some equivalent circuits. For this first state where output is high, right here, we can equivalently draw this as the RC we see here, and this is very familiar, we've seen this before. And then as we transition to our next state, we'll notice out drops low. So our next state is this low portion of the waveform, and that's going to have an equivalent circuit as seen here. Now this circuit doesn't really look like it does anything, but remember we'll have some initial conditions on this capacitor, and so there will be some transitions happening. Now if we were to just draw the equations for each of these circuits, here we've labeled them VA of C3 and VB of C3. We notice that they're familiar, we've solved things like this before, but there's two unknowns in here. We have this capital VA and this capital VB. So we can just draw the general shape of this to tell what those are. Right, as we start out giving this positive voltage like we've seen before for this equivalent circuit, the output is simply going to rise. So this average value, this voltage right here at this node, is simply going to rise with some time constant until we transition into our second state where we have this equation, and our voltage is simply going to droop like that and fall down. And then we're going to turn V out on again and transition back up to this circuit, and we're going to increase a little bit, and then we're going to turn off and transition back down and droop some more. And so VA is this voltage level right here. That's this lower peak, and VB is this voltage up there. That's the upper peak. And so at this point you can imagine we have two equations here, this bottom one and this top one. We could solve these for what is VA and what is VB. You know, what is our peak to peak on this going to be, and how do we get that to be really small, right? Because as we make this smaller and smaller, we're going to approach a straight line more. That's fairly complicated, and that's a difficult way to analyze this circuit. It's not going to work very well. You're going to get stuck. Now, just as a note, if we look, when this is a straight line, VA equals VB, and we have the average value. But we don't want to analyze it this way. It's going to make things very difficult for us. So what do? The easiest way is to look at this circuit in the phasor domain instead of looking at it in the time domain. And what that means is that we use our phasor equivalence for all the elements. So this capacitor turns into 1 over j omega c. Our resistor stays as R, and we can simply write an equation for phasor V out as it relates to our phasor V out as it relates to our phasor V in. Remember, this V out here is actually input to our circuit. And now we can evaluate this at different frequencies. First of all, if we evaluate it at DC, so how does this pass average values, or how does it pass constant values? Well, we enter in omega equals 0, and we have VC3 of 0 is just going to equal 1 over 1, that cancels, times V out. So we're going to pass the average value of the input to the output without doing anything to it. So that's a really good start, and that's what we wanted from this circuit. Now if you'll notice, as omega increases, the magnitude of this is going to get smaller and smaller. Right? As omega gets large, the bottom of this is going to get large, and we're going to have 1 over a large number. This is going to be some value approaching 0, meaning that we're going to attenuate all the high frequency components of V out. which is exactly what we want to do. We only want to keep the DC component. Now we can look at a frequency spectrum of our input voltage here, this Vout, to make things a little bit clearer. Now if it's a square wave, you'll see at DC we have some energy here at 0 frequency. And then we have some energy here at 1 times the frequency, and some energy here at 2 times the frequency, and so on. And the energy is decreasing as we go to higher and higher frequencies. Now you can see these as either the magnitude of Vout evaluated at this phasor frequency, or you can see these if you write this voltage here, this Vout voltage, as its Fourier transform. Any way you like to write it, you end up with this frequency spectrum showing you some amount of energy in the average component and then some amount of energy in the higher components. Now if we were to take that frequency spectrum and on top of it plot the magnitude here, so this is how much we're going to filter, you end up with this pink line, and you can see that our DC component we won't attenuate. We're not going to filter that at all, but every increasing frequency we're going to filter more and more. So easier to look at this in the frequency domain. Look at it with phasor analysis. So if you're going to try and solve for R3C3, what you might start with was taking a look at this equation. Say you wanted to attenuate this first harmonic by 5 times. Say you wanted it to be 5 times smaller. Well, you can solve for this. You can solve at what point does VC3 over Vout, and these are phasors, at what point does that equal 1 over 5 at this frequency? And so you're going to get then 1 over 5 equals 1 over J. This omega is that first frequency, so that's going to depend on what encoder frequency this is, times R3C3 plus 1. And you'll simply solve this for R3C3 because those are our only unknowns. Now what value do we use for omega for our encoder frequency? Well, we should use the minimum value of omega that our motor will give us. Why do we do that? Well, because if omega is larger, we're going to attenuate more anyway. So the best case is when omega is large, but we want to make sure that in the worst case, when omega is very small, we're still attenuating this first frequency enough. And so you can solve for R3C3 to get a value that you want, and then of course plug these into simulation and see that you do get very small ripple on your output here. And that's how we'll design our low-pass filter. Phasor analysis on this circuit. Now in the end, that'll get you approximate values for R3 and C3, but what we'd really like is simply simulate this in LT-Spice and find values for R3, C3, which keep the ripple on your speed. So that's that, right? Your speed's going to look something like this, and there's some average value in there. Your ripple is the difference between these two. You'd like to keep that ripple to be about 5 to 10% of your input voltage. So keep the ripple about 5 to 10% of 5 volts. And you can play around in simulation with different values of R3 and C3 in order to get the correct ripple out there. That's how we'll design R3, C3. Remember in class how we went over R2, C2 are going to set T on. We want T on to be slightly smaller than the minimum period of our encoder output. So solve for those. And then we've just gone over how to solve R1, C1 in order to get a trigger length of 1 to 5, maybe 1 to 10 microseconds. And those are the 3 different RC constants we have to look at for this circuit.